building here is I'm starting with a theory that has two fields. One is a Lorentz connection, and the other is a Lorentz vector. And we have invariance under Lorentz transformations. And from here, I want to move to a theory where I also have omega and e. But I want to regard both that's the idea. So this is nice, but well, you're never satisfied and you want to regard both fields as components of a single connection. So here you have the connection, you can look at it this way. And here you have to add the field. And in both cases, you have these gauge transformations. And they have to reproduce what we already know. These have to be equivalent. That's the goal. And this puts conditions on what these new generators are. And if you do the calculation, you find that these new generators have to be Lorentz vectors in this sense. And so obviously the simplest choice would be to have the Poincaré algebra and just to put this equal to 0. So that's a possibility. It's not the only possibility. That's nice. And the Poincaré algebra, as you probably know, can be embedded in the de Sitter or the anti-de Sitter algebra. And each of these can be embedded in a larger algebra still. You can embed this in the conformal algebra, for instance, or you can, from here, build a superalgebra and include fermionic fields. But we're not going to go as far as that, but we will go with the anti-de Sitter algebra because, well, you can go back to Poincaré if you want, doing a non-Wigner transformation. And anti-de Sitter is nicer than de Sitter because you have the anti-de Sitter CFT correspondence and you can supersymmetrize only anti-de Sitter, not de Sitter. So we're going to use this anti-de Sitter algebra and build a gauge theory for this. So we have the algebra is J is what we know, JP, I just erased it, and PA, PB gives you back J. That's the anti-de Sitter algebra. You can actually put one sigma here, and you have that's the difference between the algebras. Okay. So A now F. You have to compute this. You have to write dA plus A squared, and dA is the derivative of this. A squared is this commute with itself, 1/2. So I'm going to write only an indication. And here you have to use the algebra. And so you have J times J will give you J, J times P gives P, P times P gives back J, etc. So you have to compute this, and the result So what you have here is that the torsion appears as a component of this large curvature. And here's the Riemann curvature, and here's two field. So this is what we were calling the curvature. And this is the torsion.
That's contract is GAD, no? There is a GAD over there. GAD.
Of course,
yes.
So I think that's a pretty nice connection, that you have these both as curvature, torsion and curvature here. You don't think of them anymore as separate things, but as components of a single two-form curvature. So that's nice. Now, gauge transformations. you get Lorentz. That means that the parameter a Lorentz gauge transformation means that this parameter has components only along the Lorentz generator. It doesn't have an extra component along P. And if you compute this again, it gives you exactly what we want. So this is what we wanted, that's consistency. But now there's an extra gauge transformation, which is a translation. If we choose anti-de Sitter, this is a very special translation because it's not abelian. It doesn't commute with itself, but I'm going to call it a translation nonetheless. So what happens there? If you compute this, maybe we should do it. For instance, this is the covariant derivative of the parameter. And this will give us so J commuted with P will give again P. But that's pretty straightforward. And now I use the other bracket.
Sorry, you wrote in the third line, show omega EC isn't a lambda.
Yes, it is. And here also. Thank you. Okay. This is A, this is the gauge connection, so this is omega and this is E. But this is lambda, this is the gauge parameter, the one that defines the gauge transformation. So this is lambda. So it's omega times lambda, E times lambda. And here, let me see if I got the signs right. Okay, so here it is eta BC takes this index down. It's omega AC times lambda C. And here, this one would take the A down. But before we do that, we can interchange the order, cancel the minus sign, and in the end, this term here is equal to this term there. And so what we get is the following. Here I'm anti-symmetrizing in AB because this is anti-symmetric. And so I can read off from here that delta E will be minus the covariant derivative of this parameter, and delta omega will be, there's a minus sign, so I get so these are new gauge transformations. These are the gauge transformations for translations. And so here, the field bind transforms like a gauge field with the derivative of the parameter. And the spin connection transforms something else. So the roles are now reversed. Now this is the connection, and this is something else. This is the connection for translations. So now comes the question. So we have a gauge transformation. Okay, is the Lagrangian invariant under this gauge transformation? No, it's. I may emphasize that I'm calling these translations, but these are not. You're not moving from one point in the manifold to another point, because that would be a diffeomorphism. That would be a change in coordinates. We're not changing coordinates here. This is a gauge transformation. We are staying at the same point and we're moving in an internal space, in a fiber, in the terms of a fiber band. So that's why I'm calling it a local translation. It's local because the parameter is x dependent. It's a different parameter everywhere. It's a gauge transformation. And that's a shame. Because we built this whole edifice, this structure, to turn gravity into a pure gauge theory, where we have this integration between the spin connection and the field bind, and in the end, it fails. And I'm going to show you why it fails. Take the Eisen-Hilbert diagram. In 4 dimensions. We're going to compute the variation of this Lagrangian under these gauge transformations. And to make it even more simple, I'm going to use Poincaré gauge transformations, because in Poincaré gauge transformation this is 0. This is because this here goes multiplied by sigma, this number that appears in the algebra, and if we have Poincaré, then sigma is 0 and this is 0. This is just to make the computation easier, but if we choose to compute the variation under local ADS translations, then it doesn't get better, it gets worse. Now the variation is very simple because R doesn't depend on the field line. So we get one delta here and one delta here. We interchange change the name of the indices. In the end, we get 2 times that's the general variation. Now we replace that that's a Poincaré translation. And now, of course, we need to integrate by parts to take this derivative and put it outside everything. So I'm going to do it separately. So this is what I'm going to compute. This is a normal derivative, an exterior derivative. But since this is a Lorentz scalar, I can replace it with a covariant derivative. And now I operate. The covariant derivative of the epsilon tensor is 0. That's not trivial. It's trivial that the exterior derivative is 0, but the covariant derivative has extra terms. It has omega times this. But you can show that it is 0. So we won't care about it. The derivative of this guy is also 0. That's one of the Bianchi identities. Now, the derivative of this guy is not 0. That's the torsion. And now the derivative of this guy is what we have here, and there's a minus sign. There's a minus sign because we are jumping over a free form. That's a 2, that's 1. So in the end, what we have is delta translations of L1 is I'm confused. Okay, it's 2 times this. So there are two terms. This second term is the exterior derivative of something, of this thing here. That's not exactly an invariance, but we can live with that. But this, there's nothing to do here. That's non-zero. Unless, of course, you want to put the torsion equal to 0, which some people do. But that's very tricky because torsion equals to 0 is an equation of motion. So you are using an equation of motion to show invariance, but that, I think that's a bit against the rules. So I would say that what we have shown here is that this Einstein-Hilbert-Lagrangian doesn't remain invariant under translation, but it changes by a total derivative, which is not too bad, plus something that is really bad. It's not. This is actually what McDowell and Mansouri found, that when they tried to write general relativity as a pure gauge theory, they could make it invariant only under Lorentz transformations and not under the whole atom. So is everything lost? Now, when we were computing this exterior derivative here to integrate by parts, we had that the derivative of this is 0, the derivative of this is 0, and this guy here is the one that ruins everything. And that guy is here because we have two field bias in the Einstein-Hilbert-Lagrangian. But if we had only one field bias, if this guy wasn't there, then this would be invariant. Well, but we don't have two field bias, we don't have one, we have two. But that's a nice observation. If we had only one field bias, this would be invariant. Now, let's go to 3 dimensions. There are only 2 Lagrangians in 3 dimensions. And the Einstein-Hilbert-Lagrangian in 3 dimensions has only one field bias. So in 3 dimensions, this works. pseudo-invariant because the total derivative is still there. But we can live with that. And actually, you can do it a little bit better if you combine these two Lagrangians into one. And if we combine them precisely in this way, putting 1/3 here, this Lagrangian this Lagrangian remains invariant under full anti-desiderata. So under Lorentz transformations, which is trivial because this is a Lorentz scalar, but also under these non-abelian translations. And for that to work, you have to have both terms, L0 and L1, combined in this precise combination. No other combination works. So this is called the three-dimensional miracle. And of course it's non-miracle. And the thing is, this Lagrangian is the Chern-Simons Lagrangian. It's the Chern-Simons form for the anti-desiderata.
Oh, Eduardo,
Yes?
this anti-de Sitter algebra in 3 dimensions, so it is sort of SO22.
And where we SO21 is Lorentz? Yes,
It says SO22. I see. So it has 6 generators. I see.
I'm not really sure if it was Witten who discovered this, but in this paper, Witten used this connection between gravity and Chern-Simons theory to quantize gravity in 3 dimensions. It's a beautiful paper. I recommend it to anyone. So what's the Chern-Simons law? So that's the Chern-Simons form. It's defined for any H theory in 3 dimensions, for any algebra. So if you have an algebra, and you have a bilinear form which is invariant under the algebra, such as the trace of the product of 2 generators. If you have these 2 ingredients, then you have a Chern-Simons form. So you can write a Chern-Simons theory for any algebra, for SU2, for U1, for SON. And the recipe is always this. And this expression is pseudo-invariant under a gauge transformation. You can show it in full generality. So it changes by a total derivative. And you only need these 2 ingredients. And here our algebra is anti-de Sitter. And invariant tensor, well, what is this? There are several options actually, but you can show that if you choose this here, then you get a Laplace Lagrangian. It's not trivial that this is actually an invariant tensor. You have to show it, but it's true. You can do it. And you don't need to have 0 here and 0 here. You can have different components here, and this will give you another Lagrangian. It gives you Lambda plus another Lagrangian. And we didn't actually include this other Lagrangian, which is made up only of the spin connection. Is this, but here we put the spin connection. And this Lagrangian is very special because it's not obviously Lorentz invariant because it's made of the spin connection, which is not a Lorentz tensor. So even if you contract all the indices, it's not guaranteed that this is invariant. But it is. It changes all the biatomic derivative. And it gives the same field equations as the Laplace Lagrangian. I'm not sure why, but it gives the same equation. So this is the three-dimensional miracle. This is the reason why it works, because we have this Chern-Simons form. And it's very nice that what you find is a Laplace Lagrangian. It's not something, well, you can find different things putting different invariant tensors here, but you can use this simple choice and get only a Laplace Lagrangian. And that defines a gauge theory for gravity in 3 dimensions, and this theory can be quantized, and actually it can be solved. That means that we didn't compute the partition function for this theory. So gravity in 3 dimensions looks much nicer than gravity in 4 dimensions, because in 4 dimensions there's no analog to the Chern-Simons form. So you cannot build this thing, which has such nice properties. And the thing is, we're not sure we live in 4 dimensions. Maybe it's more than 4, but it's not less than. That's for sure. So 3 is not good enough. It's a kind of very nice theoretical laboratory to investigate how things work, but it cannot be more than a toy model. So the question is, can we generalize this to higher dimensions? Can we reproduce the 3-dimensional mirror group in higher dimensions? Is there some sort of analog to this Chern-Simons form in higher dimensions? And the answer is yes, there is, but only in odd dimensions, so not 4. So nature is very special. Very odd.
Very odd. Well, Eduardo, I think there is another paper by Witten around this time where he shows that actually, even if you consider the Einstein-Hilbert Lagrangian for gravity in 3 dimensions, he shows it's equivalent to a Chern-Simons theory.
Only the Chern-Simons?
Yeah.
Only the Einstein-Hilbert?
Yes, it is Chern-Simons.
I didn't know.
Yes, it shows that actually gravity in 3 dimensions is topological.
Wow.
I can give the reference to you.
This.
It's around this time. I think it's around 87, 86.
But maybe it's for Poincaré.
Let me Probably, yeah, I think so.
So it's cosmological constant equals to 0.
I think it's from Pompeii. Yes, I think it's from
Actually, if you in any odd dimension, this is just an aside. So if you are in odd dimensions, you can look at the last of the Lovelock terms that has many r's and one figure. And for the same reason as in 3, this remains invariant under local point finite translations. So that works. But it's only the last Lovelock term, and it's only under point finite translations. You cannot generalize this to anti-Jupyter, for instance. But in 3 dimensions, this is the Einstein-Hilbert Lagrangian, but only in 3 dimensions. In 5 dimensions, this is the Gauss-Bonnet term. Okay. The general formula is like this. But that doesn't tell you much, really. And so, for instance, in 5 dimensions, somewhere here. It's a very special combination of powers of the gauge field and the exterior derivative of the gauge field with these fixed coefficients. Actually, these coefficients come about because if you take the derivative of a Chern-Simons Lagrangian, then it gives you this, where f is the curvature. And this is a topological invariant. So the Chern-Simons Lagrangian have this property that their derivative is a topological invariant. And so, for instance, you can take this Chern-Simons form, 5 dimensions, anti-de Sitter algebra. And use this invariant tensor. And what you get is this. Let me check the coefficients. 2/3 and 1/3. And it's minus 2/3. Yeah, it's minus. There's a plus. I think it's plus. This sign depends on whether it's de Sitter or anti-de Sitter. So that's why I end up there.
Okay, we can correct.
So the Chern-Simons form in 5 dimensions with these ingredients gives you a Lagrangian for gravity that belongs to the Laplace family. It has the quadratic term, it has the linear term, it has the cosmological constant, but the coefficients are not fixed. So this has to be 2/3, this has to be 1/5. And this combination of coefficients guarantees that this Lagrangian, apart from being invariant under Lorentz transformation, which is trivial, is invariant under these anti-de Sitter translations as well. And this is actually the same Lagrangian that produces a single constant curvature space-time as a vacuum solution. It has the same coefficients. So it works because it's the Chern-Simons form. So a large part of the work in Laplace gravity has been done in this particular case, where the coefficients are such that this is a Chern-Simons form, because this has many special properties. But these special properties sometimes lead to degeneracy, because there's actually like too much symmetry. And sometimes parts of the field equations do not determine the metric, and some things are left arbitrary, and etc. But on the other hand, you can take this and generalize it to include fermionic generators and build a super algebra and a super gravity in 5 dimensions with these properties, with this gravitational sector. And so it's like a whole industry. It's a very nice theory, I think. Okay, I think I'll stop now because I don't want to kill you on a Friday afternoon. But if there are any questions, please.
Eduardo, você estava dizendo que a gente discutiu segunda-feira, que você falou que observou que para Chern-Simons em 5 dimensões você não pode ter grupo de gauge SU2, né? Isso é interessante. Então ela restringe até a forma. Pode ser qualquer SUN maior do que 2, né?
Sim, uma coisa engraçada, porque você acá precisa ter um tensor invariante, que ele é simétrico. É simétrico quando você intercambia cá os generadores. Se você intercambia S com L, então aqui o epsilon permanece a mesma coisa. Mas para esse 2 não é possível construir um tensor assim. Então não tem, na teoria de Chern-Simons, para esse 2 em 5 dimensões. Ele não existe.
Interessante.
Eu ainda estou fazendo cálculo para esse momento.
Legal. Obrigado, Eduardo. Muito obrigado.
Não, nada.
Eduardo, então para saber, na próxima semana você precisa de mais algum tempo ou você acha que fez satisfatoriamente o que você queria fazer?
Não, eu acho que está bem assim. Eu poderia continuar fazendo a generalização para dimensões mais altas, mas eu acho que não.
A gente no ano que vem pode fazer algum tipo de seminário sobre isso. Tá bom, então.
Nas atividades de verão.
Nas atividades de verão também, exatamente. bom? Obrigado, Eduardo.
Então, deixamos.